Okay. Okay, Clinton, you see it good. Okay, so yesterday you should have found to be the Math Nation lesson not to be a big deal, scatter plots. You have a set of data and you graph the data. It's no different than we've been doing all year, whether we were graphing linear functions, exponential functions, or quadratic functions. The difference was that none of these tables created perfect lines or perfect parabolas or perfect exponential curves. And that's the deal. A scatter plot is scattered. It represents real life, and in real life, most things are not perfect. So what we're doing, yesterday we talked about if we could see a trend, was the scatter plot trending in a positive or a negative direction? Did the scatter plot seem to take a specific shape? And that's what we were analyzing. But today what we're doing, you're going to see a lot of what you'll see in Math Nation tomorrow as well, but I want to get straight to what we're doing with residual plots. A residual plot is a way to test an equation that was made for a scatter plot and to see if the equation is the proper model. So if you're looking at this example right here, let's get right to the example. The Watsons have always kept a garden of geometries in their yard. The data table and scatter plot below represent the number of years for their longest living geometry and how tall it's grown. So if we look at the table, the age of the tree in years, that's our X value, that's our input. And the height of the tree value, that value is our Y value, it's our output. This represents actual years, actual height. Now, if you look to the right, these ordered pairs, 1, 9, 2, 12, 3, 14, etc., are all plotted. If I didn't have the line and the parabola in place, you would see a scattered dots. Two different people, let's pretend me and Mrs. Whirl as an example. I said, Mrs. Whirl, I think that I could draw a line through the center of this data, and I think that a line, a linear model, would be the best type of equation to represent this relationship. And maybe Miss Whirl said, you know what, I kind of see some sort of a curvature here, and I kind of think that, you know, it represents more of a quadratic relationship. So let's pretend that I came up with my equation, right down here, the linear model, f of x equals 1.3x plus 9, 2. And Mrs. Whirl came up with her quadratic equation. F of x equals negative 0.11688x squared plus 2.5355x plus 7.0238. Not a lot of fun to write those equations. You're really not going to have to focus on writing the equation as much as you'll have to focus on selecting what is the right type of equation. And what you should be aware of is that you might have two linear equations that represent lines that you drew, and you're just trying to determine which linear equation is better. So it's not always that the models are different types of models. It could be a couple of the same type of model, but then you're just testing it to see which equation specifically better represents the data. If you look at it, and let me open my chat box over here. If you look at those two, my gut would tell me, looking at this, that it's linear. I mean, I'm thinking about a tree and how tall it grows, and it just seems to get taller with age. And I would not expect a parabola to be the best fit. So my initial reaction is that I would think that the linear model is the best fit or the best representation for this table. But what we'll do on the next two slides is test the linear equation and test the quadratic equation, and then create residual plots from those equations. The residual plot is what will provide you evidence that will help you determine whether the original equation was a good representation of the scatter plot. Okay, so, and not the original equation, our new equation, our that we're using to make predictions. So I'm going to go straight on to the next slide where we're going to test the linear model. So the residual plots are going to help us figure out which one is better. And let me move this out of the way. To create a residual plot, we have to calculate predicted values using our actual X inputs and the equation that we came up with. So if I came up with the linear model for f of x equals 1.3x plus 9.2, I'm going to take all of these actual values right here, and one at a time, because this is a function table, that's all it is. I'm going to take these values one at a time and plug the x values in place of x and do the math. What you have right here are the actual values from the first page, but I'm going to calculate the predicted column. Now, I went ahead, you can see half of this table is filled in because it's a long table, and I don't want you guys to sit here and watch me do all these calculations. So I filled in a bunch of them already. But just to give you the idea, if I plug 1 in place of x, 1 times 1.3 plus 9.2 is going to give me what I expect the predicted value to be. So I would expect, based on my equation that I wrote, that this output value, meaning the predicted height of the tree, is 10.5 feet. Okay, and I'll do the same thing for 2 years, 3 years, and 4 years. If I plug 2 in place of x and multiply it and add 9.2, I will get 11.8. If I plug 3 in place of x and calculate it, multiply and add, I'll get 13.1, I think. Let me double check. Yep. And then if I plug 4 in place of x, multiply and add, I'll get 14.4. So these represent the predicted height of the tree based on the equation that I came up with that I thought represented the data the best. So now what you do next is you calculate the residual value. A residual value is simply taking the actual values minus your predicted values, and that gives you the difference. So this is an important little summary right here. Residuals equal actual minus predicted. So if I take 9 minus 10.5, I'll get negative 1.5. If I take 12 minus 11.8, I'll get positive 0.2. 14 minus 13.1 equals 0.9. And 15 minus 14.4 equals 0.6. And that's the exact same thing I did down here, 17 minus 15.7, and so on and so on and so on. So this is a table that I'm using to calculate residual values, actual minus predicted. Now, what I'm going to do with these values is plot these differences on a graph. You can see it doesn't look like the graph on the first page. This graph is just representing the differences between actual and predicted, and those differences are called residuals. So I know that at 1 year, my residual value was negative 1.5. So I'm going to go plot 1 year, negative 1.5. 2 years was 0.2, like right around here somewhere. 3 years was 0.9. 4 years was 0.6. 5 years was 1.3. So maybe up about here. 6 years is 1, right there. 7 years is 0.7. 8 years is negative 0.6. So that's going to be right about here. And 9 years is 0.1, very tiny right here. Okay, so what I can see so far is that I see most of the points, most of those residual points are above 0, and only 2 points are below 0. The thing with a residual plot is that a residual plot wants to have a scattered look to it. The fact is that I kind of see a pattern here. And to me, if I drew a line, or if I tried to trace this pattern, to me it looks like a curvature, almost like a parabola. And I'm going to put a very important note right here that patterns on residual plots, and this is what I always tell everybody, patterns are bad. On the first page back here, we're looking at a scatter plot. So when you draw your model through the scatter plot, you want it to follow the pattern. But a residual plot is something where hopefully your differences, your residuals, are not very large. If you have very small residuals that are close to zero scattered above and below the line, then that means that your equation actually is a good fit for the scatter plot. If you see a pattern happening, then that tells you that too many of your points are going in a certain direction. In other words, your differences are not close enough to zero to make it a good fit.